Modern AI has given us these, genuinely revolutionary tools.
Oh, absolutely.
We're talking about sophisticated RJ applications. That's retrieval augmented generation that can pull an answer from thousands of pages instantly.
Or those huge AI agents that write code right alongside you.
Exactly. But here's the secret that, I think most people miss. The real challenge isn't actually the intelligence of the LLM.
No, it's not the brain.
It's the infrastructure. It's managing this massive, just constant flow of inference requests being sent to that model.
The plumbing.
The plumbing. And if you're an organization running mission-critical stuff, you just cannot tolerate bottlenecks.
You can't.
The collection of sources we dove into today, they use this brilliant analogy to help us understand how one open-source project is solving this scaling nightmare.
And it all comes down to air traffic control.
Yeah, that's it.
Think about it, right? Your local airport handles wildly different flights. You have these small domestic planes.
Yeah, short hop flights.
Yeah, those are your quick ride queries. They need a simple runway, fast turnaround, but then you get a huge, fully loaded international jet.
That's your massive agentic coding assistant request.
Exactly. It needs specialized handling, way more compute time, a much longer runway.
And if the airport, or in our case, the infrastructure, just tried to send all those different planes to the same few runways.
It would be chaos. Immediate, catastrophic gridlock.
Right.
And that's exactly what happens with naive scaling. So the role we're focusing on today is the air traffic controller, the system that has to understand the request, see the real-time capacity, and route that plane to the perfect runway.
And that system is LLM-D, Large Language Model Distributed.
It applies that precise, intelligent routing to AI inference.
So the D for distributed is really the key here. LLM-D is designed to let organizations run these powerful LLMs faster and, crucially, cheaper.
By intelligently distributing that workload.
Usually across something like a Kubernetes cluster. The whole point is to get ahead of the congestion before it can even form. So let's look closer at that congestion problem. If you're running an inference server, maybe using a popular engine like, say, VLLM, you're just constantly getting hit with these varied requests.
They do not look the same at all. You might get a request from a user querying a huge internal knowledge base.
Okay.
So that request has a really large input token count. You're summarizing 100 pages, but you only need a small, quick output.
That's your little domestic R8 flight. Needs to be fast.
Right. And then right behind it, here comes that big agentic request, a developer using a coding assistant in real time.
This is an ongoing conversation.
It's an ongoing conversation. It needs high context, low latency for the entire session. If your system treats those two completely different requests the same way, you fail.
And your costs just go through the roof.
They skyrocket.
And the standard solution, the one that actually causes the problem, it sounds so simple and appealing on the surface. It's just round-robin balancing.
Precisely. The naive approach. Just send the next request to the next available server.
Assuming everything is uniform.
But it's not. And that leads directly to that gridlock, because your small, quick request might get stuck idling behind a massive one that just started processing.
So the system isn't using its resources intelligently at all.
Not at all. It's using them uniformly, and that's the mistake.
And for the user, the consequence is immediate, and it's super frustrating. That congestion shows up as something called intertoken latency.
Yeah, and that's not the time it takes to start the response. It's the pause, the stutter between the words as they stream out.
It feels slow, clunky.
It feels broken. It's like talking to someone who pauses for 5 seconds between every single word.
Unusable. But what's really fascinating here is how the source material points out this opportunity for optimization before the request even hits the main router.
Yeah, because a lot of these LLM workloads, they're doing similar things over and over, summarizing the same documents, processing similar code snippets.
So a lot of requests contain similar content.
Or they require similar chunks of text in their pre-processing.
That similarity is gold. Because if you can spot those overlaps, you can use techniques like prefix routing or caching.
And the benefit is huge. You save money on hardware acceleration because you're not recalculating the same thing again and again.
And you increase throughput.
Dramatically. By routing requests that share those common prefixes together, the hardware only has to calculate the new part. It's a foundational efficiency step.
Okay, so if that standard round-robin approach is the problem, how does LLM-D fix it?
It introduces a really sophisticated gatekeeper. The sources call it the Inference gateway.
And this isn't just a blind router.
Not at all. It's an evaluator. It actively assesses the incoming prompt before it decides where to send it.
This sounds like the core intelligence. The actual air traffic controller.
This is it. It doesn't just check if a runway is free. It routes the plane based on dynamic predictions.
Okay, so what is it predicting? What are the metrics?
We can break it down into three crucial things. First, the current load of the request itself, its size and complexity.
How big is the plane?
Right. Second, the predicted latency. The system actually calculates how long it thinks this request will take based on its size and what the whole cluster is doing right now.
Wow. Okay.
And third, the likelihood of the data already being cached. It's leveraging that prefix routing opportunity we just talked about.
So it's looking at the past,
Yeah.
the cache, the present, the current load, and it's predicting the future, the latency.
Exactly. It's this real-time, three-dimensional decision.
That sounds like it would be a heavy calculation in itself.
Yeah.
How do you make sure the gateway doesn't become the new bottleneck?
That is the key architectural challenge they had to solve, and they did it by making the calculation extremely lightweight. It's handled by a specific component called the endpoint picker.
So it's a separate little brain.
It is. Its only job is to manage the metadata and the routing calculations. It's not running the model. This keeps the prediction part from adding overhead.
That makes sense. You separate the routing brain from the processing muscle.
And that endpoint picker uses those calculations, the load, latency, and cache, to manage the request in two very distinct phases.
And this is where it gets really interesting. This is the part that I think is revolutionary.
The disaggregation.
Yeah. LLM-D doesn't treat the request as one single process. It splits it, or disaggregates it, into two optimized workloads.
And those two phases are prefill and decode.
Okay, so what's the difference?
Prefill is the first step. The system is evaluating the incoming prompt, taking in all those input tokens. This requires a huge amount of burst compute power.
Like firing up the jet engines.
Exactly. Then decode is the second phase. That's where the model is actually generating the response tokens one by one back to you.
And the efficiency gain here is profound because these two processes have totally different needs.
Fundamentally different hardware requirements. Prefill is basically one massive math problem, a matrix multiplication. It's a burst task.
So it gets routed to special hardware.
Yep. It's routed specifically to use high-memory GPUs. It needs a lot of resources right now, but for a short period.
So the high-memory GPU does that initial heavy lift. It understands the context. Then what?
Then the decode stage, which is just generating words sequentially, that's much less memory intensive, so it's allowed to scale separately.
Often on different, maybe lower memory GPUs.
Right. Because that task is sustained, it's not a burst. You get much greater concurrency.
Yeah.
You're only using your most expensive hardware for the moments you absolutely need it.
Okay, but if prefill and decode are running on different servers, somewhere in a Kubernetes cluster, how do they stay connected? How does it not lose context?
Ah, that's the connective tissue. They both share the same KV cache, the key value cache.
Which stores the state of the model.
Exactly. The high-memory GPU does the prefill, it writes the context to that shared cache, and then the scaled decode process picks up right where it left off.
So the cache isn't just for speed, it's what enables the entire distributed architecture to work.
It is. It lets you manage this distributed inference without the cost of running every single instance at peak capacity all the time. So powerful. So we've covered the nuts and bolts. Why does this matter to you, the listener? Especially if you're designing these high-demand AI apps.
Yeah. At the end of the day, it all translates directly into performance, into meeting the service agreements that businesses depend on.
And we can actually quantify this impact. The numbers are pretty startling.
They really are, because they hit the most painful bottlenecks. Let's start with P90 latency.
Right. So for anyone managing these systems, P90 is the metric that matters. It ignores all the easy, fast requests.
And it targets the bottom, slowest 10%, the ones that make customers leave or cause you to fail your SLOs, your service level objectives.
And this is where LLM-D showed an improvement of.
3 times. A 3 times improvement in P90 latency.
3 times faster for your absolute worst case scenario. I mean, that's the difference between a viable product and a failed one in an enterprise setting.
It really is.
But what about the user's feeling, that feeling of speed?
That's time to first token.
When you're using an AI assistant, a chatbot, if you have to wait even half a second for that first word to appear, it feels broken.
No matter how fast the rest comes out.
Doesn't matter.
Yeah.
And the data shows LLM-D increased that speed by a massive 57 times.
57.
What's that?
It's not an incremental improvement. That's a fundamental change in the experience.
It is. Your interaction goes from waiting for an assistant to collaborating with one instantly.
From a roadblock to a partner.
And if we connect this to the bigger picture, these aren't just nice-to-have improvements. They are critical for meeting quality of service agreements. QoS.
The kind that large organizations and hyperscalers absolutely require.
For any mission-critical AI workflow, this level of controlled, intelligent throughput is becoming the definition of reliability. The transition we're seeing here is fundamental.
From uniform to intelligent.
We're moving away from treating AI requests like uniform data packets and toward this workload-aware routing. It's a shift from an assembly line to a highly choreographed ballet.
That's a great way to put it. So that brings us to the end of our deep dive. We've seen how LLM-D acts as this predictive air traffic controller for AI.
Using dynamic metrics load, predicted latency, cache likelihood.
To efficiently distribute these really diverse workloads, especially on platforms like Kubernetes. And the result is these massive speed increases, particularly for the slowest requests.
And for that crucial first token response time.
Understanding this level of intelligent traffic control, it really shows you what's powering the fastest, most reliable AI applications that you use every single day. It's enabling a level of performance that just wasn't possible with the old way of thinking.
You know, the central concept of LMD is treating resources and requests dynamically based on their type and load, not uniformly. And that raises a really important question for the future.
Okay.
As AI workloads get more complex, more mission-critical, how many other traditional IT infrastructure problems, from network management to database queries, will need to adopt this kind of dynamic, predictive air traffic control methodology just to function at scale?
So this isn't just an LLM thing.
I don't think so. The future of reliable, high-scale computing might look a lot less like a uniform factory and much more like a perfectly choreographed airport.